All right, so happy to have Sasha give the second talk.
Yeah, as I said before, please do interrupt me to ask questions. So today we'll sort of, I'll actually get to what might deserve to be called p-adic Riemann-Hilbert, but today there's not going to be a complicated base variety. It's all going to be happening over a point. Now, since we're in an arithmetic setting, even local systems over a point is an interesting object. It's representations of the Kalman group. But let me actually go one step back and let me once more recall the complex Riemann-Hilbert correspondence, because it will be somewhat motivational. So the complex Riemann-Hilbert. So if there was a complex complex manifold X, and there was a C local system on it, then, as Christian explained to us, there was an associated vector bundle of flat connection, which was defined, maybe there was not a notation, but let me call this RH of L. It was the transfer product of this thought of as a locally constant sheaf with the structure sheaf. Okay? And the reason this was a vector bundle of the same rank as L was that locally, for the analytic topology, or the only meaningful topology on X, C was a constant sheaf, so locally it was just a trivial bundle. Right? But now suppose I'm trying to compute sections of this sheaf, not just locally, but over maybe some slightly larger base. So how would I go about doing this? So let me write down the following expression, which might seem somewhat idiosyncratic from the point of view of complex geometry, but it will be motivational for the p-adic story I'll try to explain. So suppose I have some open, and I'm trying to compute sections of this bundle in this open. Okay, so how do you compute sections of a tensor product of sheaves? Well, in general, it's not just tensor product of sections, right? Which is why it's interesting. So one way we could compute this is we could first move to a setting where, say, the local system is trivial, and for that it would be enough to go to the universal cover of U. So let's utility be the universal cover. Let's say I choose one. Let me call this map F. So then, how do I compute sections of this bundle on U? It suffices for me to compute sections on U tilde. Then there would be a natural action of the fundamental group of U on this U tilde. Let me suppress a base point, since I already chose a universal cover. It's tantamount to the choice of a base point. So sections on U would be exactly sections on U tilde, which are invariant for the section. Okay? So how do I compute sections on U tilde? So let me put in parentheses sections on U tilde, and then I'll take invariance for the fundamental group. But, well, on U tilde, this local system becomes trivial. So if I just tensor the constant sheaf of the structure sheaf, it's just a bunch of copies of the structure sheaf, but let me write it more canonically. So I can tensor, so if I go to U tilde, then on U tilde, my local system is trivial. Wait, let's go in this F. So if I take global sections, then, so this is not the end of the formula yet. If I take the global sections, then this will be a vector space of the same dimension as the rank of L. And this is just a complicated way of writing the representation of the fundamental group of U associated with L. Well, to L restricted to U. All right, but then I tensor it with functions and I take global sections. So I'm just going to tensor this over complex numbers with functions in this universal cover. And what's inside the parentheses would be global sections of this tensor product of sheaves on U tilde. And then I take invariance back to go to get sections on U. All right. So the structure of the answer is that I have my representation of the fundamental group. I tensor it with some large ring on which the fundamental group also acts, and then I take invariance in the tensor product. You might notice that Alice was doing just that in her construction of beta. And the trick was to choose an interesting enough ring here. And let me just finish this analogy by saying that this was RH of L. Well, as I've written, it's just the section is just an abelian group, but this was actually a vector bundle and it had a connection So why is it the vector bundle? So it's a module over functions on U. And well, here I do have an action on this. I have an action of simply invariance of O of U tilde under by 1 of U, because I can multiply elements. And this is just functions on U itself. And similarly, since U tilde was a complex manifold in itself, there is a drum differential acting, which gives me the connection. Right? So with this complex story spelled out this way, let me proceed to the p-adic situation where I'll claim it will formally look equivalent. But before I do that, are there any questions about my rephrasal of complex Riemann-Hilbert? Okay, so now let's move on to the p-adic story. So as in Alice's setup, so yesterday, just to save time and space, I was working over QP, but now let me work over an arbitrary discretely valued p-adic field. So for me, what this means is that K is the result of inverting P in a ring OK, where OK is a complete discretely valued ring, where the maximal ideal induces the residue field, which is some characteristic P field, which is perfect. So you won't lose anything if you just assume that K was QP or a finite extension of QP, but I want to emphasize that this works in this generality, and I will never use finiteness of the residue field. In some other parts of p-adic geometry, there are arguments which would exploit. Okay? And so we want to study local systems on, so etal QP local systems on spectrum of this field, which is the same as representations of the Galois group, or continuous ones. Okay, and so we're trying to set up some analog of Riemann-Hilbert correspondence, and so the first approximation to this will be this functor d de Rham, which Alice has already mentioned. So let me just put it back on the board. So this functor d de Rham from QP representations of GK. To filtered vector spaces. And the definition of this functor was that if I took a vector space, if I took a representation V on which GK acted, I'm supposed to tensor to this large ring and take invariance. And so how do you think about this procedure? Let me tautologically rewrite it slightly, because maybe for some purposes it will be more intuitive to think about it this way. So if I tensor to represent a finite dimensional representation of anything else, and I take Galois invariance, it's the same as taking Galois covariant Holmes from the dual representation into the second factor. So if you like this functor, it looks at all possible ways of mapping this Galois representation into p de Rham. And so representations for which this will give me a non-zero value are representations for which the dual can be somehow mapped to p de Rham. So if you think that you can think of p de Rham as a humongous Galois representation, and d de Rham it's detecting whether your V or its dual lies in this gigantic representation. All right. And so the key interesting feature was, right, and so the filtration on this output, it was defined as the analogous invariance for these filtered pieces. Okay? And so the key property was that if I applied d de Rham, well, say to etal homology of any smooth variety, so x over k smooth variety, then this recovers the de Rham cohomology of its Hochschild. Okay. Now, well, I mentioned that at the end of yesterday that a function like this is probably doesn't quite deserve to be called a p-adic Riemann-Hilbert correspondence. Well, on many levels, but for instance, there are plenty of representations which get killed by this function. So let's give an explicit family of examples. So maybe I'll state a certain computation which will not yet be obvious from the definition, but hopefully we'll learn how to do these computations by the end of today. So L is defined as cyclotomic character, so the character of the Galois group into ZP cross, which records how the Galois group acts on roots of unity. Now let me pick some p-adic number such that it makes sense to raise the cyclotomic character to this p-adic power. So, for instance, for any k a inside, which is congruent to 1 mod p squared with 2. Okay, so I'm just saying that let me choose an a so that on the image of the cyclotomic character, the binomial power series expansion of raising to the power a converges. For instance, for any k already or for qp, any element congruent to 1 mod p squared would work for this. Right? So what will happen if I apply the function d-Deron to this power of the character? So if a was an integer, so for instance, if a was a negative integer, then this character really literally appears as, say, homology of a projective space in an appropriate dimension. And it turns out that the output will be that this function will give me a one-dimensional vector space K, and the filtration will record the weight, the power to which I raise the cyclotomic character. So the filtration, right, but except that there is this switching of the sign, so the filtration will jump in degree minus A. So is equal to all of K, and then the next step of the filtration is okay. So maybe a mnemonic rule for the switching of the sign is that positive powers of the cyclotomic character, they don't appear in homology of varieties, but rather negative powers of the cyclotomic character do appear. And so negative powers of the cyclotomic character get carried to filtered modules where the filtration jumps at positive indices, okay, as the Hodge filtration does. But now I sort of indicated at the end of yesterday that if A is not an integer, then this functor actually, well, right, there is no way this functor reasonably outputs a one-dimensional space in this, and in fact, and we'll prove this by the end of today, that this functor outputs 0 if A is not an integer. Okay, so we see that it clearly, it kind of forgets, doesn't like the characters which are not integer powers. And let me just make a remark, it's a general property that for any representation B, if I apply d-Deron tuning, then this will be a vector space whose dimension over K will be at most the dimension of the original representation. It's not formally obvious. And if here the equality is attained, then I'll call a representation Deron. If these things are functional. And in particular, all representations arising from homology of varieties, they are Deron. But for instance, all these powers of cyclotomic character for non-integral exponents, they're not Deron. Okay. Now, if you're looking at this, is there a question? If you're looking at this, you might suggest that, well, this probably indicates that there is some finer invariant, which actually gives me something meaningful for all representations, and I just haven't told you what it is. Okay. So let me actually tell you what it is. And this will basically, let me first say how the invariant will look like, but the way we'll construct it will basically be a step in the process of trying to compute the invariance in this tensor. So, So here's how this finite structure will look like. So I'll suggestively denote this function RH for Riemann-Hilbert, but I'll call it RH plus, and in a second I'll explain what plus stands for. And yeah, let me say that I think this really is all, it all goes back to the work of Fontaine and Sen. I think in this particular formulation, it's due to Fontaine. So it will be a functor from QP representations of the Gaulliger. To the following category. So let me introduce the following notation, which Alice sort of already introduced implicitly. Let me work over a slightly larger field, and the significance of this field I'll try to explain. So let me take the field k infinity, which is the result of adjoining to k all roots of unity. Sorry, all p power roots of unity. So it's a union of finite extensions of k. So just an algebraic extension of k. And so my functor, it will go into finite free modules, say m, over the power series ring in one variable over k infinity, equipped with, maybe somewhat surprisingly, a flat connection. Well, flatness is immediate here. So it's a map from M to M tensor. Well, this tensor product, I'm just tensoring a free module of rank 1, but it will be suggestive to denote it the way I'm going to do it. So let me tensor it with a free module of rank 1, with generated out node by dt over t. Okay? And this should satisfy the property that connections satisfy, the Leibniz rule. So the result of applying nabla to a product of an element of this ring and an element of the module is the sum of just taking A out of the nabla and M tensor the differential of A. So it's a connection, but I allow a degree 1 pole along T equal to 0. And this is exactly the kind of object that appeared in Christian stuff. And let me even connect it further to, so this is the target of the functor RH plus, but if I so want, I can further forget the exact choice of an integral lattice over this Taylor series ring, and I can invert T. And there would be a functor to, well, modules, well, really vector spaces over Laurent series field of over k infinity with a connection with regular singularities. Okay. So you notice that if I invert T, I get a bona fide connection, because now any pole is allowed, and it will have regular singularities because here the pole was logarithmic. And the nice properties about this functor will be that RH plus, that it preserves rings. So whatever Galois representation you feed into it, it will output a module of the same rank as the Galois representation was. And for instance, it will be compatible with tensor product. People will know it. Where here, well, there's this additional structure of the connection, and the connection on the tensor product is the usual way you define the tensor product of connections via the Leibniz rule. So connection here will be connection of P1. And now what does this have to do with this d to run? Well, it turns out that d to run, at least, well, it's a k vector space, but this function will not quite recover the d to run itself, but it will recover it if I extend scalars to this larger cyclotomic extension. And there, it will be obtained from, so I have to apply this RH plus, then I'll invert T to get a module with connection regular singularities, and I should just take flat sections of it. All right, so yeah, so this functor just inverts T. So this was a RH plus was a k infinity square brackets t module. I invert t. It's a modular Laurent series ring with flat connection. So just a vector bundle of flat connection over a punctured formal disk, and I take flat sections. And this immediately, if you trust this, this immediately explains this property. Because if I have a rank n modular flat connection on the formal disk, it has at most n-dimensional space of flat sections. And so you see that in this language, V is the norm. If and only if this vector bundle of flat connection has as many sections as the whole rank of the bundle, which means that it's generated by its flat sections. But it just means that it's trivial as a bundle of connection. So it's just isomorphic to a bunch of copies of this vector space where the differential or the connection is simply the de Rham differential. So I've produced a functor which now at least doesn't kill any representation. And now somehow the non-de Rhamness of the representation is recorded in the non-triviality of this connection. And so, well, here really, if you like, I somehow artificially introduced connections to the picture, but I think considering this story over a point really be motivational for the story I'll try to tell tomorrow, where we'll work over a more complicated basis, where there'll also be a connection in geometric direction. But today, my goal will be to explain this picture. Are there any questions about the goal? Please.
So here, like when you take flat sections, you can only do it globally. There's no like local way to do flat sections, like in Riemann-Hilbert.
Yeah, if you like, yeah. Well, I mean, yeah, it's a.
Do it locally? Actually, you just only do it globally.
Well, here I literally mean flat sections in the sense that it's a vector space over this field, and it has a k infinity linear in the morphism, and I take kernel of that. Yeah. I mean, you're right. So maybe what you're getting at is that when I say a connection, really I have to specify what I mean by differentials here. I don't want to take abstract scalar differentials of this. I really just want one-dimensional module generated by dt. So I want to remember the topology on t. But I'm just going to do this in this ad hoc way, by just declaring that my module of differentials is this.
It's like relative to k infinity.
Right, but I'm saying for it to be literally relative to k infinity, I have to remember the topology on t. It's literally
I see.
I'm just explicitly saying what.
Is that why you have the dt over t there? Can you explain?
Why it was a dt over t?
Yeah.
You mean as opposed to?
It's just dt.
Well, for me, it would be equally surprising if it was dt here. Well, I think when I explain where the connection comes from, we'll sort of see that this happens. So maybe one way to explain this is that the failure of the connection to preserve so the failure of the connection to preserve this fixed lattice over the Taylor series ring will be related to my representation having non-zero Hodge-Tate weights. So whenever you feed, somehow the defect will, its size will have to do with Hodge numbers of the. So say if it was a representation in this form, it will have to do with Hodge numbers of the original, of the variety of which you're taking, the color representation of which you're taking. Alright. So let me try to explain where the structure comes from. So I think Ellis already alluded to this idea that if I'm trying to analyze this de Rham functor, I'm taking invariance under the whole Galois group. And let me try to do this in 2 steps. So here is the next thing I'd like to say. So let me first of all, so here I'm studying this functor v tensor b de Rham, and let me remind you what Ellis just said. What was the structure of this ring b de Rham? So b de Rham had a filtration, which was z indexed, and it was decreasing, and the well, it was complete with respect to this filtration. The filtration was exhaustive, and the I graded piece was isomorphic to the ith twist of, well, right, yeah, Alice's notation is better, let me use C rather than CP. This was a Gaussian covariant isomorphism. And so so the fact that this filtration is really non-split Gaussian covariant, and this is an important and interesting feature of the situation. But let's first of all just try to stick to working with C. And let's try to analyze the tensor product of V with C over QP and how the Gaussian group acts on it. So Alice explained to us that if V was a representation coming from homology of varieties, then this gets a Hodge-Tate decomposition. And it turns out that, well, the representation there will just be a direct sum of cyclotomic characters acting on C. All right, so let's try to analyze this action first. So let's even first do an even more basic example. So let's consider the following situation. So let's try, maybe trying to address, well, in a very maybe unsatisfactory way, Daniel's question of how you come up with these things. Let's just try to experiment and let's try different things in place of V rho and see what kind of functions they would produce for us. So what will happen if I tensor V? So following the analogy with complex Riemann-Hilbert where I just erased, there I was tensoring with functions on the universal cover of my base. So the universal cover in algebra would just be the algebraic closure of it. So let's see what will happen if I tensor this and try to compute Gaussian invariance. Well, how does the Gaussian group act on K bar? Well, it's just a union of finite extensions of K. So this is just product with the union of finite Gaussian extensions. And my Gaussian group acts on each of them. But now, what is this L as a representation of the Gaussian group? It's a theorem of the normal basis that any such L is just isomorphic to the regular representation of the Gaussian group of L over K. Okay, for any finite Gaussian extension. So then it means that I have this increasing union of regular representations of finite quotients of the Gaussian group, and I'm taking these invariants. And so how is this going to look like? So I can take this union to the outside, and well, so suppose I'm trying to compute invariance of V tensor L for a given L. But now, so the action of GK on L, it factors through this finite quotient. And so if computing invariance, then it's the same as first taking invariance for the absolute Gaussian group of this whole L, which now acts only on V. And then there is an action, there is a regular representation. And I'm taking the residual action of the finite Gaussian group. All right, so what's happening here? I have a finite group. I have some potentially arbitrary representation of this finite group, but I tensor it with a regular representation of this finite group. It's a general fact that if you have a representation of a group and you tensor to a regular representation, what you get back is just the direct sum of a bunch of copies of a regular representation. So invariance here will be canonically identified with just this space, regardless of how the Gaussian group acted on it. So let me put this here. So I would want, I can probably swap these boards, right? So this will just be the union over all finite Gaussian extensions of invariance under these Gaussian groups. So in other words, this just picks out vectors in V on which the Gaussian group acts through a finite quotient. So you see that if I just took this as a candidate for my p-adic ring, I would get back something rather small. And so most representations arising from geometry, they would have few Gaussian invariants. For instance, Alice was studying representations coming from abelian varieties, and if an abelian variety has a good reduction, then there'll be no Galois invariance at all. So the invariance here, there is this very small space. Are there any questions about this computation? Okay. So then, what will change if I go up to C? And so Alice indicated that things change drastically, and somehow, in particular, this example of abelian varieties, it showed that if you transfer the representation arising from an abelian variety with C, then there you actually do get some Galois invariants, even if you didn't get them over K-bar. So how do we work with this thing? So I introduced this field K infinity, and let me study the Galois group of K in 2 steps. So let me consider the Galois group of K bar over this K infinity. So I'll note this by HK. And so it's an open subgroup, it's not an open subgroup, it's a subgroup, it's a rather closed subgroup of GK, which is the kernel of this economic character in GK. Right, because here I've exactly adjoined all roots of unity. And the quotient of GK by HK, I'll denote by gamma K, and its economic character establishes this as an open subgroup of ZP groups. It might not be quite all of ZP cross if my K already contains some roots of unity. Okay? Oh, so great. Yeah, this group HK is rather large, and this is just an open subgroup of ZP cross. It's a one-dimensional p-adic Lie group. So let's first study the action of this HK. And there is the following striking sounding result. So, this is why I wasn't supposed to do that. So it's a theorem which I guess in its generalities was proven by Sen, but I think it also Tate proved a large part of it, which is the following. So suppose I have a finite dimensional CP vector space, or C vector space, which is equivalent to an action of this group HK. So now the subgroup of the Galois group, which is continuous. So it just means that the action map as a map of topological spaces is continuous. So here, if I choose a basis for W, it would just be isomorphic to a direct sum of a bunch of copies of C, and C has its own p-adic topology, and I'll just get the induced topology. It's independent of the choice of basis. It's continuous, but it's not acting by automorphism of C vector space, because HK also acts on C, and I want this action to be semi-linear. So an example of such is, let me first say what it means to be semi-linear. So if I have an element of this vector space and a scalar in C, then this acts via, so H can act on A because it's acts on C. This will give me this. So it's a semi-linear action. So the main example is, the way we're going to apply this is that if you had an action of HK on some QP vector space, and the action was literally linear, and W then is the product of P with C, where the action is there. Right? So suppose I have such a gadget, then actually claim that there is only one isomorphism class of such things. So then W is just isomorphic to a bunch of copies of C. Well, however many the dimension of W allows, as an HK representation. So, of course, there could be plenty of different representations on QP vector spaces, but I claim that they all become isomorphic if I transfer the situation of C. Right? So, before I say something about how this is proven, let's just try to contemplate this a little bit. So, this would be really, really false if instead of C, I did just K bar. I didn't p-adically complete my field. And this is what the computation over there shows. So, an example pertaining to that theorem is that if I took, so well, if V is any finite dimensional vector space with an HK action on which HK doesn't vector a finite motion, then, as this computation shows, V tensor K bar will never be isomorphic to a bunch of copies of K bar. Because if it was isomorphic to that, then then even HK equivalently, this would have a basis. Then this would have a basis consisting of HK invariant elements, which is not the case if V didn't have a basis of elements on which HK acts for a finite quotient. Right? But somehow magically this becomes true over C. Well, technically this is possible because C has more elements, and it turns out to happen. So let me briefly say where this comes from, because really this is this principle, which at this point it might seem kind of arcane, is really what powers essentially all of p-adic quad theory. So notice that on this board something similar has been happening. So here, what was happening here? Here I took in this tensor product, this was some vector space in which this finite Galois group was acting in a possibly interesting way. But then I tensored it with the field L itself. And there, because it was a finite extension, I said that this was just a regular representation of this finite group. And the result resulting tensor product was completely independent of the representation I plugged in, right? It was exactly of this shape. It was just a direct sum of a bunch of copies of the field. So for finite extensions, this works perfectly. And this is actually a special case of a much more general statement, which is called descent. So let me state it in not maximum, but slightly larger generality. And this will explain what will happen there. So, do it here. So, a lemma, which is a special case of Étale descent. So I'll need it for a slightly larger class of rings than just yields, so let me state it for arbitrary commutative rings. So suppose I have a finite Étale map of rings. And suppose that it's even a Galois cover. So it's a Galois for some finite group G. Okay, then suppose I'm exactly in this setting. So I'm given, let's say, a projective module which I'll call M, and I'll have a subscript S to emphasize that it lives over S, which is equipped with an action of G, which is semi-linear. All right? So it interacts with scalars from S exactly by this formula. Then this module actually has the form some projective module over R, which is simply translated up to S from R, and the action of this finite group is purely on this S. So for some M over R. Right? So this is a special case of descent, because I have this module MS over S, and the fact that it's equipped with the semi-linear action of G is the descent datum for this map from R to S. And then it gives me, it canonically defines for me an R module M, and a part of the descent. So what it means for M to be a descent of MS is exactly that this equality holds. All right? Are there any questions? Daniel?
Is there a reason MS is projective?
No, just for my application it will be projective. Yeah, it would have been true for any module. Yeah. Just to preserve the analogy with vector spaces. Thank you. Right? Any other questions? Yep. So how does this help us? Well, here we really have this humongous extension k bar over k infinity, And there's this p-adically complete p-adic completion of k bar, so there doesn't seem to be any finite detail extension inside. But actually there is. And here is the key statement. So I'd like to preserve my supposed Riemann-Hilbert functor on the board. So this is called an almost purity theorem. So in fact, in generality, I'll state it, it's a bit of a misnomer, but let's just keep it this way. So, well, sort of in this form, it's due to Tate, but somehow tomorrow it will reappear, and then the formula will reappear, it will be due to Falding's. And, well, maybe full generality due to Schultz. So what is the statement? So I have this K infinity. Let me take this dichotomic field. Let me take any finite extension of K infinity. No worries. So it's without any finite extension. Right? So just an algebraic extension of fields. Now let me, well, this K infinity is equipped with evaluation, and there is a unique way to extend this valuation to L. So I can talk about the ring of integral elements in L. It's all elements in L whose valuation is non-negative, right? And the claim is that the map from all K infinity, which is also integral elements, to OL, is what's called almost at L. Which means, so it's just a term, which means for me that if I took the relative Kähler differentials of OL relative to OK infinity, right? So etal means that relative Kähler differentials are 0. Here it will mean that this module is not literally 0, but it's very small. So it's a module over OL, and its torsion, and moreover, it's killed literally by the maximal ideal of OL. So is annihilated by maximal ideal of OL. So by all elements whose valuation is positive. So what kind of statement is this? Well, here, if I took a finite extension of local fields, so discretely valued fields, if that extension was ramified, then the module of the differentials, well, it would be some torsion module, but it would be a non-zero module, because on the whole ring of integers, by definition of what it means to be ramified, the extension will be not at all. But here I'm saying that whatever L was, maybe L was obtained by adjoining a lot of roots of uniformizers and so on. This module will be very small. It will be, well, will not be literally 0, but it will be annihilated by any element of arbitrarily small validation. So it seems rather counterintuitive. So let me not give you a proof of this, even though this is the key fact behind all of this theory. Let's just consider an example. And the example will involve some... It will involve some cheating. Just because make things more explicit. So, yeah, let me keep this here. Alright, I think the Riemann-Hilbert will go. Oh, no, actually, I think I can fit the example here. So, this field K infinity, there was something special about it, but the analogous statement was true for other extensions of K. Let me not specify what exactly this class is. If you're curious, that's what's called perfectoid fields. Well, up to p-adically completing that. But let me just say explicitly, it's also true for another field. So this is also true for field K infinity prime, which I'll define as the result of adjoining to K, not of the roots of unity, but over the roots of P. So it's the union of all extensions obtained by adjoining P power roots of P. Okay? Also true for K infinity prime in place of K infinity. Okay? So I'm claiming that if I took any finite extension of this field, then on the law of integral rings, this will be almost at all in the very same sense. So let's see how this plays out. Alright, so actually I do need to erase. Okay? So let me just, for simplicity of notation, let me take K to be QP. So now my K infinity prime is this field obtained by adjoining all chosen roots of P power order. Now let's just do an example of one particular L. So let me assume that my P was larger than 2. There is an obvious modification otherwise. And let's say that my L was obtained by adjoining further a square root of P. Right, since P is odd, I haven't yet adjoined the square root of this level. Now let's see what I'm saying here. So if I join the square root of P to just QP and took the ring of integers, so if I took the ring of integers of QP, I join square root of P. This would be ZP, I join square root of P, and it's a ring over ZP, but it's not an étale ring. And the modulo of differentials, well, it's torsion, but it's large, so let's just compute it. So it's generated by a single element, so it's spanned by the Kähler differential of this element with the condition that, so the defining relation on this element that its square is P, and so there is a condition that dP, which is 0 because it's an element in the base ring, ZP with respect to which we take the differentials, P is the square of the square root of P, so it's we take the derivative of the square. So this differential of square root of P is annihilated by twice the square root of P. Well, 2 is invertible also. Okay, so it's some torsion way. But now I claim that if I did the very same thing, if I took this extension over that K infinity prime, the situation would be different. It would be a torsion module, but it would be killed by arbitrarily small powers of P. So how does this happen? The point is that once I've adjoined a lot of ramification to K itself to create K infinity prime, I could rewrite this extension L as not adjoining the square root of something of P, but adjoining a square root of something of arbitrarily small valuation. So let's notice that here I easily computed the ring of integers of QP adjoining square root of P, but if I work at this infinite level where I already have a lot of other roots of P, the ring of integers has some unexpected elements. So inside OL, there is an element which I'll call P to the power 1 over 2 to the power Pn. So why is this? Well, because I can rewrite this as P to the power 1 over 2 times P to the power 1 over P to the power n, which is already in my ring, but then raised to this large power. So if you do the algebra, it's going to be an element of this form. So if I join both square root of P and all P power roots of P, then I also get square roots of P powers. Okay? And since it's an element of positive relation, even though I wrote it as a fraction, it does live in the ring of integers. But now notice that adjoining that element is the same as adjoining the square root. But then you see that differential of P to the power 1 over 2, it's the same as the differential of this new element. Well, times whatever this thing is, but it lies in my base ring. So inside the module of relative Kähler differentials, this will be equal to, I can just move out this element to the outside. D to the power P 1 over 2 power 2Pn. Okay? But now, by the very same computation as what I did here, this element is killed by a much smaller power of P now. So this is annihilated by this very small power of P. And now I could iterate this argument for every n, and I would learn that my element in Kähler differentials is killed by this arbitrarily small, these arbitrarily smallest powers. And I was able to make this maneuver because my K infinity already had enough P power roots. Okay. So are there any questions about this computation? So I have to admit that I really rigged the situation for this to be as trivial as possible. In general, it's a much more interesting kind of computation, and really sort of doing the analogous algebra is it's equivalent, if you like, to computing p-adic periods of certain representations, well, depending on what your L is. And in general, well, I think this is, any other examples would be less expensive. So now I claim that the same works for the cyclotomic extension. How does it help us study representations over C? So let me maybe in the interest of time not explain that. Let me just say it's a rather formal argument. I'll just claim that I can reduce, so the idea of the proof is that I'll use this almost purity and this property of descent along étale covers, and I'll apply this to lemma about descent plus almost purity imply the analogous statement to the theorem, or almost analog of the theorem, for when I'm not working with C vector spaces, but rather I'm working with modules over the ring of integers modulo any power of p. And then by taking the inverse limit along n and inverting p, the word almost disappears, and you get the statement we actually want. So if you're curious about details, ask me, but I claim that now it's more of a bookkeeping. So at least you see that some finite étale covers appeared in the picture, and so we're in a position to apply this descent. Okay, so let me now, in the remaining, suppose 7 minutes, say how this allows me to study the Galois action and the stanza product. So let's get rid of this.
While you're erasing,
Yeah.
is the Hamilton complex of like a well over infinity almost exact?
Exactly right. That's exactly right. Yeah, you're right. And technically, there should be an almost version of the lemma which I just erased. Okay. So right. So what was my goal? So I was studying the stanza product, and I was interested in the study of the Galois action. But now let me just use that as a as a HK module. This is isomorphic to a bunch of copies of C by this theorem. But now there is some right. But now let me pass to invariance under HK, and as another way of stating this theorem is that this C vector space is spanned by HK invariance, so it's isomorphic to a bunch of copies of HK invariance inside C, however many copies I need. Now, it's hopefully intuitive that kind of there is a so it's essentially by the same token as the solved purity, the invariance in C under HK. It's the p-adic completion of this ring of this field K infinity. So clearly, all the elements here they do lie in the invariance, and again by the analogous arguments, there are no more elements in the invariance. Right, K infinity itself was not a p-adically complete field because I would join infinitely many algebraic elements. But now what's interesting is that there is this remaining action of the group gamma K, and since I only have so much, just to and I'll now trade this action of gamma K for this connection on this module over a formal punctured disk, and really by the end of tomorrow or the day after tomorrow, I'll try to convince you that this gamma K is analogous to the action of C cross, which appeared in Daniel's lecture. Okay, but let's take it one step at a time. So what's my situation now? I have a fairly simple group. It's an open subgroup of ZP cross, and it acts on this vector space. And the action is still semi-linear, right? Because gamma K acts on K infinity. So first of all, I can get rid of the hat. Let me just state that I can do this. So there is a decompletion, this module. So there exists a natural module which I'll call H of B, such that, which is a K infinity vector space. Again, with a semi-linear action of gamma K, such that this module, it's just the result of completing this back. Okay? But now I'm claiming that once I've done this, this Galois action on h of v, even though it's semi-linear, it's really very close to being linear. And what I mean is that so it's an action of ZP cross, and I deliberately referred to this as a one-dimensional p-adic Lie group, even though I didn't have to. Because now what we're going to do is to really make this into an object of linear algebra, because so far it's still a semi-linear action. We're going to take the differential of this action, and we'll try to define the induced action of the Lie algebra of this one-dimensional Lie group. So let me define an operator phi on h of v. This phi is sometimes denoted theta, and I think this was the original notation introduced by Sen, and Higgs field is also denoted theta, and it's not a coincidence. I'll try to see that, but to make us less confused, let me denote it by phi. So phi of any vector. This will supposed to be the action of the generator of the Lie algebra of the ZP cross. So how do we define the action of Lie algebra given an action of a Lie group? Well, we differentiate. So let me write the usual formula for the derivation. So it will be a limit over elements of this Galois group tending to infinity, where I would act on an element v by gamma. I would subtract v. And now, well, gamma is really just an invertible p-adic number for me. So, I mean, this embedding is via the dichotomic character. So let me divide it by this. All right? But now, magically, you can see that the operator which I wrote now, it's now it is actually a literally linear operator. So first of all, I claim that it's a well-defined limit, and then after this is granted, I claim that this is a linear operator because if I tried to multiply v by a scalar, the scalar from k infinities would lie at some finite level, it would lie at some finite extension. So it would be stabilized, the scalar would be stabilized by an open subgroup of the Galois group. So in this limit, I would eventually get into this open subgroup. And so I would be able to move it out of my gamma. Right? So I've got a k infinity linear operator, and which it loses some information about the Galois action because it really only cares about how kind of the germ of open subgroups of unity act. And so maybe I'll get back and recap this tomorrow more thoroughly, but let me just, to end, let me write down a formula for what this bundle with connection is going to be. So my goal was to define, to attach to V, this module RH plus of V, which is supposed to be a module over k infinity double bracket C. And it was supposed to be equipped with a connection. So I'll define this tomorrow, but let me just say that what I've defined so far was the mod T reduction of this RH plus of V. And ultimately, the connection which I'll define will be, this phi is the result of multiplying the connection by T to make it regular and reduce it mod T. So I've already defined for you, so my goal was to define this module of connection. I've defined basically its residue, what it does on the fiber mod T, and tomorrow I'll try to lift it to RH plus of V. And you might imagine that here, since it will both C, to lift it like this, I'll have to invoke beta-ram or beta-ram plus. But ultimately this connection will arise from the action of the Galois. So, sorry for ending slightly midway, but maybe I'll start with a recap of this tomorrow.
Maybe I should wait till tomorrow. You gave some p-adic topologics that give you connections with regular singularities.
Yeah.
I'm wondering if there's anything that maps to more general connections with irregular.
Right. Not that I know of. Yeah, it's kind of, we'll hopefully see tomorrow that this this condition on regular singularities, it's kind of related to Griffith's transversality, that somehow the connection displaces the Hodge filtration at post 1.
Can you remind me why you get like K infinity?
Where do you get K infinity where?
Like, so why is like K infinity the natural state rather than RH plus?
Oh, right. So as my discussion of almost purity hopefully indicates, this would have been fine for any perfectoid field here. So the key property which I used about K infinity is that the HK action was completely understandable. So I could have, and people do this, I could have done this for larger perfectoid fields, and I could have done it for, say, the perfectoid field which is the result of adjoining all roots of P. Well, this maybe, this is kind of a different, this will be a different linear algebraic setup, because now this is not a Galois extension of K, so there's some descent datum, and you can work with it. And well, it's a fruitful perspective to keep in mind all perfectoid extensions simultaneously, and somehow this is really what's being embraced by modern p-adic Hodge theory. But this is, if you like, it's a random choice.
Sorry if I missed this, but did you say why there's a plus on RH?
Oh yeah, I didn't. Thank you. It was just an indication that this is a module over the non-punctured formal disk. So my notation for my notation RH will be reserved for what happens if I invert. Yeah, thank you.
So for this HV, we kind of lose this HK action. I mean, like whatever the HK action is kind of gone. We do not remember it.
If you like, yeah.
So, but if we have this RH plus, then do we like still kind of recover? Can we recover this?
No, it will also be in a sense lost, but so somehow for RH plus it will also be constructed through a similar observation that if I tensor, basically literally the same will be true. If I tensor V with B to RUM, then as an HK module it will also be trivialized like this. But somehow, really, I mean, HK does play a role here, because how do you compute this action of gamma K in this module? So I first have to compute these invariants. And invariants here, well, HK acts very non-trivial on both sides. So to come up with an invariant, I really have to invoke, as Alice was calling them, some p-adic periods from C. And I have to take linear combination of elements of my Galois representation with coefficients in those periods. And what combination I take there will depend on how HK was acting. So I might have some representation whose which factors through a quotient of the Galois group, which corresponds to a field which is completely linearly disjoint to the cyclotomic extension. And yet its p-adic Hodge theory would be very interesting. I mean, the functions of p-adic Hodge theory on such a representation will give you something interesting.
We'll just sort of push the poster session back, 10, 15 minutes. So those of you who have posters obviously need to set them up. There are easels in 724.